Hi, everyone, and good evening, and welcome to our special presentation from the Brown Planetarium here at Ball State University. We're going to be doing the first ever Astronomy Slam tonight here with students from Ball State. I'm Dana Thompson, the director of the Brown Planetarium here. If you haven't been before, we do have the largest planetarium in Indiana, and we typically open it up for public shows. Unfortunately, we can't do that right now, so we're going to be bringing you the universe online virtually. So we're really excited to have all of you here with us today to cheer on these students while they present their passion of astronomy with you all. So we have 4 students with us. We have Alec, Neal, Belle Wines, Melanie Isenbarger, and Ricky Gorby. And they're going to tell you a little bit about themselves before we jump right into the presentations. So Alec, go ahead first.
Hi, my name's Alec Neal. I'm a graduate student here at Ball State, and I do research in astronomy and specifically binary stars, which you're about to find out more shortly.
Great, thanks, Alec. Belle, go ahead.
Hello, I'm Belle. I'm a senior at Ball State. My major is chemistry with a concentration in biochem, and I'm going to have an astrophysics and biology minor. I also do research with Alec in the Barrington group, and I've also done research in biology.
Thanks, Belle. And then Melanie, go ahead.
I'm Melanie. I'm a senior at Ball State. I'm majoring in both physics and astronomy with a minor in Spanish, just for fun. I also do research. I think all of us do research together, so it's been good to work on a challenge with a competition.
Thanks, Melanie. And last, we have Ricky. What's up, Ricky?
I'm Ricky Gorby. I'm a graduate student here in my last year. I also do research with everyone else here on binary stars.
Great. All right, so each of these students are going to have 10 to 12 minutes apiece to share a bit of the universe with you tonight. And then after all of the presentations, we're going to get you a link to a Google form where you can vote for Astronomy Slam Champion. And the champion gets this award right here. And we were going to do this event back in April. COVID kind of shifted things a little bit, so we're excited to do it here tonight with you. All right, so first up is Alec. If Alec, you want to share your screen, make sure your video is optimized and you're sharing your sound, we can look forward to seeing your visuals. What you got?
All right,
take it away.
Good? All right, I'm Alec Neal, and I'm going to be presenting on eclipsing binary stars. Specifically, the picture in front of you is an example of a binary star, and you'll learn more about it as we go along. All right, so first off, I'm going to show you a video that shows you a pretty intuitive and visual example of what these things are all about. So as you see, when one of the bright objects, which is one of the stars, goes in front of the other, you can see a noticeable dip in the brightness because the stars are pretty opaque, meaning the other light is not really getting through. And this is what's called an eclipsing binary. That just means that one of the stars, or the stars themselves, eclipse each other because they are getting in the way of each other as we see them orbit around each other. And this system is actually called Algol, and more affectionately named the Demon Star. And what's cool about this one is actually sort of a trinary star. So you can see in the back there, around here, that's actually another star in the system. So this is actually a 3-body system. But the inner close to ones are very good examples of eclipsing binaries, or an uneclipsing binary. All right, so binary star, to make it more formal and scientific, so to speak. They're stars which are gravitationally bound, so they're not just stars that look close and you think that they're, oh, let's call them twins. No, they have to be orbiting around each other, sort of like how we orbit around the sun. The difference is that these sizes, the sizes of the stars, are actually very similar in that we're in the sun or the solar system. It seems like everything is orbiting around the sun, but what's actually happening is that there's a part inside of the sun that the whole system is orbiting around. And that you can call the center of mass. So you can see here, that little dot right here, that's going to be the center of mass for this system. So it's a little bit different than what you're used to in things that just orbit one single body. They can be as far apart as several hundred AUs, which is a fancy name for how close we are to the sun, and then as close to being physically touching. So you can see up here is an example of one that's touching. And despite looking at stars and they all look singular and whatnot, you might think, well, binary stars must be pretty rare, but they're actually not. Binary stars in general take up about 50% of the total stars that exist, but that's kind of a rough estimate, but they're not as rare as you might think. So eclipsing binary stars, kind of go back to that. You saw in the example with Algol, they're situated so that one of the stars actually goes in front of the other, and then vice versa. The other one eventually does that too. So as you saw in the video also, this causes the light from the system to vary and block each other. This varying brightness can be plotted versus time and can produce what's called a light curve. So down below here, you have the light curve of a binary star system. The red dot is just sort of the time sort of variable. You'll see some more things in a minute. You can see on the left brightness. So it goes up to about 100% brightness, and then it dips to about almost 60% brightness. So if it went all the way down to 50%, you could imagine, well, 50% is only half the system. So that means that in this system, only or almost half of the system, in this case, a single star, is being blocked. So importance of binary stars. Binary stars actually give us the only direct way to measure the masses of the sun. When I say direct, I don't mean, we're going to take a scale and just put the stars on there. It's more of a concrete, we know this for sure, so to speak, way. And the sun is an exception because we orbit around it. We have other methods, etc., but we don't orbit those other stars. So we can't necessarily tell those other ways that we determine the sun's mass. So how we do that is called Doppler spectroscopy. And if you've seen the analogy or whatever, so when a fire truck or a train's coming towards you, the sound will be noticeably higher pitch, and then when it goes away from you, it starts getting deeper in pitch. That's because the sound waves are kind of shortening because they're getting compressed, so to speak, as they're going towards you, and then they're expanding because they're trying to go towards you, but they're also going away. You can see in this diagram how we actually tell is when something is coming towards us, the light will actually be what's called blue shifted, and then once it goes away, it goes through what's called red shifting. So we can tell from how much red or blue shift each of these stars go through, but we can tell how fast they're going in their orbits. And that can actually tell us how much each of them weighs relative to each other. Eclipsing binaries, you can also do this, but it also allows us to discern other characteristics and ascertain, make certain the system as a whole. So for example, it can tell us the inclination or how they're angled. So if you, like in the other example, almost 50% of the light was being blocked. So that can give a clue to like, well, if that's the case, then the inclination must be almost directly on. So that's the thing. And the way you sort of do that is you can imagine you're just making a 3D model of the system, and you're just seeing, well, what geometry would make this light curve just from it moving around each other. What's also nice about these is that it's not really time sensitive, despite it being a very fast event, but that's actually a good thing because they're short periods. And learn a little bit more about that in the future. So it's also really cool is that these close binaries, because they're so close, their gravity can sort of disrupt each other. And these binaries can help us understand stellar evolution. So, for example, here's an example of a binary star. One method that we use to measure how consistent the star is throughout its orbit, because you would imagine the period to be the same. That's not always the case. So you can see here on the right, observations back from 1775 up until the present. And what you're seeing is you're seeing a constant change in the period of the system. So if we say when the two stars, or if one of the star eclipses each other, we can say that's a time of minimum. So that's a point where we know that should happen, and then the next one should occur at whatever we think the period is. We can see here, this actually reflects the transfer of mass from one star to the other, and we'll learn more about that in a second. So here's an example of what's called an algol type. That's because algol is an example of this, and it's just another term for detached binary. So they're very close, and they eclipse each other, but they're not touching. And you note how the brightness is at a maximum except when they block each other. Because you can just see in the visual representation, the light shouldn't change because nothing's occurring. Here's a close contact binary. These are the ones that physically touch. These are called W Ursae Majoris variables, or W UMA. And that's because W Ursae Majoris is an example of a star, and they just decided to name it after that because it was just a good example, a well-known example. Because they're touching, you might imagine them to be sort of similar because they can share stuff, right? So that in that case, their temperatures are very similar. And because they have to be so close, their periods are very short. These stars usually have periods less than a day. And you can see on the right here, the shape of the stars are heavily distorted. The other stars were more spherical, like you would imagine, like our sun is spherical. But these ones, the matter is being sort of sucked into the other because of their proximity. And another one, you saw the plot thing when I was talking about the times of minimum stuff. So this one is an evolved system where one of the stars has become extremely big. It's called a giant or supergiant. These giants don't necessarily change in mass, but because they get bigger, they become less dense. And so that means that they're less able to carry all of their gas that they have around them. And because they're part of a binary system, the more densely packed star can begin to suck some of the matter from the other one into what's called like an accretion disk, or torus, as this calls it right here. And then that O minus C diagram you saw, that's actually telling you how fast the transfer of matter is going. And you can see here, here's an example of the actual system Beta Lyrae. And Beta Lyrae is like the W Umas in that it was named after the star that was an example of it. And that's it. Here's another system where you can see the light curve and then the physical representation of it. Yeah, that's it.
All right, thanks so much, Alec. If anyone has any questions for Alec, go ahead and put them in the chat, and we'll do a questions and answers session at the very end. Go ahead and stop sharing your screen, Alec, and we'll get ready for the next presenter. So Belle's up next. Belle, go ahead. Make sure to optimize your video and share your sound.
Hello. So as you guys know, I'm Bella. Nice to meet you. And hopefully you guys can answer my question. I'm going to have you guys think of 5 scientists. It could be in any field. You just have to think of 5. So I'll give you a little bit of time to do that. Okay, do you have your 5? Out of those 5 people that you thought of, were any of them women? If the answer is no, it's okay. Can you think of any women scientists? If the answer is no, you're not alone. A study conducted in 2014, they polled over 1,000 people and only 75% of people could. So out of the 25 that couldn't, to them, they thought the levels was pretty weird. And out of the 75% of people, the most answered one was Marie Curie. And they speculated that the reason because of that is because there was a cancer center named after her in the region that they had been testing. So they thought the name recognition was just due to the fact that this cancer center was there. I would like to hopefully increase the number of women scientists you can think of, and primarily just in the physics and science realm, because that's what this talk is about. So to start off, the impacts these women have made was the first one had defined the spectral classification for stars. So she figured out a way to put stars into categories. And the next one discovered the first strange phenomenon that they hadn't really seen before. They had thought that an object like this could occur, but they had never seen it. And then the last one experimentally showed that supermassive black holes are a real thing, and they're just not a theoretical idea that are possible. So the women that we're going to be discussing today is Annie Jump Cannon, Jocelyn Bell Brunel, and Andrea Ghez. So first off, Annie Jump Cannon. She was born in 1963 and died in 1941. A fun fact about her, she was a suffragette, so thank you for your contribution. She was a part of a group of women named the Harvard Computers after she had graduated with a physics degree. This group of women were hired on by Edward Pickering to produce a Henry Dapper catalog, which what they wanted to do was collect observations from the southern hemisphere to categorize stars to see the similarities and differences between them. Her alongside Antonia Murray, they had sort of fashioned this catalog that Annie Jump Cannon gets credit for. Using this catalog, Antonia Murray used it to compare and found the relationship between the spectral type of the star and the size of the star, so I think that's a notable contribution. And Henrietta Leavitt used things that Alec had talked about in his talk about how you can find masses using variable stars and binary star systems, which another fun fact is Henrietta Leavitt and Annie Jump Cannon were both deaf, so they kind of bonded over that when they were doing their research together. So the research that Annie Jump Cannon had done was using spectroscopy, which is the study of interactions between matter and electromagnetic radiation. The spectral type that she had used is absorption. So what the absorption lines are is when you have, let's say, a hydrogen, and there's a photon that hits it, and it's just the right color or just the right frequency or wavelength for it, and it can jump up to an excited state. And to have it jump up, it has to steal that photon. So that's why here in the example here, that there's just random chunks missing, and that's because electrons of hydrogen, for example, just steals it, so it's no longer in the spectrum. This bottom image shows the classification system that she did form. It's in two different categories. It's in letters, and then the second subset is in numbers. The gnomon, to remember the OBAFGKM, is O be a fine girl / guy, kiss me. O is being the brightest or the hottest, and M being the coolest and the dimmest. The only real defining characteristic of her categorization or her classification is that A0, so the hottest type of A, is defined by the strongest absorption of the Balmer line. So the hydrogen's being excited to the second state. Okay, and the next contribution we're going to talk about is Jocelyn Belle Brunel. She was born in 1943. She got her physics degree from Glasgow in 1965. She got her PhD from the University of Cambridge in 1969, and when she went to grad school, she went to go study radio astronomy, which was new, and not a lot of people have done anything in that field since it was only discovered in like the 30s, like early 30s. So she went to go study quasars under someone named Antony Hewish, and during this time, she had noticed that the interference that she had got was out of the ordinary, and it wasn't just noise. So this was something that she had seen, and this is something she had seen, and it was more dramatic than just everyday just noise, I guess, to show. So what you can see on the left is what she actually found. So they thought it was kind of a blip, and her professor didn't really think that anything was right. He was like, no, you must have done the wiring wrong, since she had built this observatory and this telescope. So, and then she was like, no, literally, like, this is real. I don't know what's going on. I think it's something. So he had come back, and shortly after they were knocking through what could these blips be, she had found a second one. So the object that she found is called a pulsar. And how it works is it's a neutron star that has really strong magnetic fields, and it produces a jet that comes out since it's moving so quickly. And so this jet can be seen, it's sort of like a lighthouse. So once the jet's in your view, you can see it, and then once it's out, you can't, and it's very periodical. So that's how you see these sort of bumps at the bottom. The Nobel Prize was awarded for this, but it was not awarded to her. It was awarded to her professor in 1974, along with another professor there at Cambridge. So this video will show the magnetic field lines. You can see that shows it's so strong. And a lot of these pulsars are very quick moving. The period that they go around is about a few seconds to a half second, and the most is like about 7. Let's say the next individual we're going to talk about is Andrea Gay. Yes, she was born in 1965, and she used the idea that Alec talked about to find mass of objects using a system. So she had done this by taking observations from stars that are by Sagittarius A, which is the black hole in the center of our galaxy. Her notable, famous, favorite star that she has is this one right here. It's the little red dots, and it's also the yellow one over here. And that one's her favorite because it only has a 16-year period. So with this, she experimentally proved that the black hole in the center of our galaxy is supermassive and it's not just a normal black hole. And she found the mass of this black hole to be about 4.1 million times the mass of our sun, which I think that's pretty incredible. She received the Nobel Prize for this year, alongside, she split it 50-50, well, 25-50 with the person who theoretically thought of it and proved that it could be possible, named Sir Roger Penrose, and then split the experimental side with Richard Ginzel. She's the fourth ever woman to receive a Nobel Prize in physics, and one of the first ones being Marie Curie. So I hope these women have been an inspiration and shown that women can make an impact in astronomy and physics, and they should be more represented in science. Thank you.
Thank you so much. And if anyone has any questions, go ahead and again put them in the chat. We'll do questions and answers at the very end of the presentations. We have 2 more presentations this evening. And next up is Melanie. Melanie, go ahead and share your screen. Make sure to optimize your video and share your sound with us.
Is it working?
I see it.
Okay, cool. So as Dana said, I am Melanie Isenbarger, and today I'm going to be talking to you a little bit about sound in space. So to get started talking about sound, we have to take a look at how do waves work. We know that sound is a wave. We actually know that sound is a mechanical wave, as you see here. And a wave is just a fancy way of saying how energy travels. So waves carry energy. So there are more than 3 types of waves, but today we're just going to be focusing on these 3 that you see here. So we'll start with the mechanical wave. You'll say it says, or see that it says medium necessary. So what does this mean? It essentially means that for a mechanical wave to travel, it has to travel through matter, and matter being a solid, liquid, or gas. So for example, when we think of a mechanical wave, we think of a seismic wave. That's a vibration through a solid. Or a water wave, which is a vibration through a liquid, or a sound wave is actually just a vibration through a gas. So the next type that we see here is the electromagnetic wave, and you see it says no medium necessary. It doesn't need anything to travel. This is why we can see light coming from space. It can travel through the vacuum of space. It doesn't require anything. It's pretty much traveling around and through everything around you. And the last type we're going to talk about today is the gravitational wave, which is a relatively new thing that we'll get into later. And essentially, the gravitational wave will travel through space-time itself. So when you think of a wave, there's something that we call frequency that I think Belle maybe touched on a little bit. But another way to think of frequency in terms of a sound wave is pitch. So this here is the frequency that humans are actually able to hear. But a better way to think about it is like guitar strings. So the lower the frequency, typically lower the pitch, and the higher frequency, the higher the pitch, or essentially how tight or loose the waves are. So that just gives you another way to think about it. So is there actually sound in space? We know that space is a vacuum, but we also know there are things out in space. There's Earth in space, we're in space, there's lots of gas and dust all around. So we do know that space is not a perfect vacuum. But we also know that the universe is so large that the density is basically 0. We know that if you added up the mass of everything in the universe and divided it by the volume of the universe, it's basically 0. And that's what we call density. So even if there is sound in space, most of it would be above or below human hearing range, so we probably wouldn't hear it. So that leads us to believe, can we hear it? Generally, no, unfortunately, but maybe fortunately. So if we take a look at a black hole, we see sort of a disk around it of gas and dust. And this is just a simulation here. Unfortunately, we don't have any videos like this for real yet. Maybe we'll get there. But we can still analyze a lot of observations around black holes. So for example, we know there's a supermassive black hole in the Perseus cluster. And recently, NASA's Chandra X-ray Observatory studied the waves that were traveling through the gas cloud around this black hole. And we realized it was producing a frequency in terms of sound that would be 57 octaves lower than middle C on a piano. If you're not musically involved, that's about 1 billion times deeper than any human could hear. So essentially, no, we could not hear it. But we know that there are these objects in space. There is matter in space, or medium in space in certain places. So what if we travel to these objects? We were right next to them. We were able to be within the area where there's matter, not between objects, but at an object. So for example, a black hole, we see there's lots of gas and dust all around. There's also supernovae and collisions. So on the left, you can see that gas cloud kind of expanding out from the supernovae, and the collisions, both of which seem like they would be extremely loud, extremely violent sounds. But in reality, for example, here, when you saw the matter kind of, or the gas explode out, that it exploded out so quickly and dispersed so quickly, again, because the vacuum of space and the size of space is so large that, again, your density would basically be zero unless you were right there. And if you were right there, I don't think you'd be around to talk about it or say that you heard it or prove it. So let's say we travel to a different object, a solid object, something we could actually stand on. If there's no atmosphere, maybe you could potentially hear it, but only if there was seismic activity within the planet and your ear was physically pressed to the ground, because that's how we actually hear. There's a bone that sort of vibrates in our ear that we then kind of turn into sound. So maybe if that movement was occurring and you have these perfect circumstances, so maybe there's something to the phrase, keep your ear to the ground, but for the most part, it's not gonna work. So let's say, okay, we know sound requires an atmosphere or medium. What if we go to an object that has that? Would we hear sound? Well, sure. We know that sound depends on the environment or the elements that make up the atmosphere. So for example, let's say we travel to Venus here. And just based on the picture, we can see it's extremely hot, super thick and dense of an atmosphere. And because of this, it would cause a slower vibration of our sound as we would speak. Theoretically, if we could even, visit there. But it's much harder to move or vibrate denser particles, so your voice would actually sound significantly lower and you would have a very bassy voice. But again, because the atmosphere is so humid and full of moisture, it actually travels faster through liquid, so your voice would be a little bit squeakier than it is normally. And again, because this atmosphere is made up of so much carbon dioxide that it would actually dampen or muffle your voice, so you would sound a little bit quieter. So this is mostly carbon dioxide. The Earth is nitrogen, for example, about 80% nitrogen, I believe. So let's say we travel somewhere a little more similar to Earth, like Mars. So we know, just based on pictures and rovers and things like that and information that we've received, that Mars is extremely cold. And we know that cold air is more dense, which again would cause your voice to be significantly lower or bassier. But we also know the atmosphere on Mars is significantly less dense. So your voice would be a little bit more husky or raspy, like a good jazz singer. But again, a lot of this atmosphere is made up of carbon dioxide. So your voice would be a little bit more muffled because carbon dioxide absorbs sound a little bit quicker. So last but not least, forget about the planets, let's travel to a moon. So we have Titan here. Again, we know Titan's extremely cold, super dense, but it does actually have an atmosphere that is similar or comparable to Earth's atmosphere in terms of elements. So because Titan's cold, once again, your voice would be a little bit lower and the density is higher. So again, you'd have a little bit more husky voice, but because nitrogen absorbs less sound, your voice would actually be louder. So it might sound like you were yelling all the time. So there would be sound theoretically if you could be on these planets without a spacesuit on. So again, maybe it's a good thing that there isn't sound traveling in space, because if there was, the sun would be producing sound of about 290 decibels. So maybe you could hear it and then you probably wouldn't hear anything ever again. For reference, 140 decibels is a jet engine, and 180 decibels is a rocket launch. So significantly louder than both of those things. And the thing that we all are really interested in is, what would the space battle sound like? So would it sound something like this? So that's really what we're all used to seeing. But if we really kind of think about it in the things that we've been talking about, if you were in the ship that was destroyed, you would probably hear it because things had been hitting your ship and you were breathing the air inside the ship. So maybe if you were in that ship, you would hear it. But again, if you were that close, you're probably in trouble. But if you were in the ship that had attacked the other ship, you wouldn't hear that ship explode at all. It would be totally silent. I know that's not very exciting, but that's okay. But if shrapnel from that ship maybe was hitting your ship, that sound would be created by the vibration of your ship and would be able to travel through, hopefully, the air that you are breathing in your ship. So both ships maybe individually could hear if they had been hit, but anywhere in between, if you hit the other ship, you're not going to hear anything. And again, that's how it works. If you were to be wearing a spacesuit and something hit your spacesuit, that vibration would be created on the surface of the suit and would be able to travel through the air and you would hear it. So if you believed that you could hear an explosion like that, don't feel bad. So if anybody's played asteroids or seen movies, a lot of times we're taught that this is what space would sound like, or a battle in space would sound like. But now you know that that's not the case. But don't feel bad if that's what you thought. So another way we can use sound to our benefit is to turn light waves into sound. So these electromagnetic waves that we talked about in the beginning, and turning them into sound that we're able to hear. So essentially, maybe you have a radio in your house. That essentially works by converting these electromagnetic waves into mechanical vibrations that we interpret as sound. So maybe you've seen the movie Contact and you remember this scene. So there we see that radio telescope that Belle actually mentioned in her talk. And this conversion of electromagnetic waves into sound is what we call data sonification. So it can really help us interpret things and information and light in a way that we otherwise wouldn't be able to. But also it's just kind of cool. And sometimes you can do things in science just because they're cool and just because you can. So another way that we can study space, again, is by turning these electromagnetic waves into sound. So if we were to do that, this is what Earth would sound like from space. Kind of weird, that's not usually what you normally hear. Saturn, for example, this one's a little scary, so if you're by yourself, I apologize. That sounds like a Halloween soundtrack to me. If we were to take a listen to the sun, again, converting electromagnetic waves into sound in the range that we're able to hear. It's more of just a low hum. If we were to take a look at a moon, for example, like Io, the moon of Jupiter, it would sound something like this. And to me, that one sounds a little bit like a windy day, which could be the case because we know storms are very, very strong on Io, which could be producing these radio waves. And last but not least, if we take a look at that last type of wave I mentioned, the gravitational wave, we can actually convert gravitational waves into sound. So LIGO actually, I mean, what's cooler than one black hole is two, but I guess it ends up being one after they merge. So this is what it would look like if two black holes merged. And this exact thing actually did happen, with both of these black holes being about 30 times the mass of the sun. So they were extremely large. This was an extremely powerful event, which is how we were actually able to detect these gravitational waves. And this event released 50 times more energy than every single star in the observable universe combined. So it was extremely powerful. That's the only way it really traveled all the way here, because again, gravitational waves do not require a medium to travel. So this is what we detected at LIGO. With the first set being the exact frequency that they detected, they didn't have to edit it in any way. That's exactly what it would sound like. And the second one just being a little bit easier to hear. But I like to think that they did it because chirp chirp for Ball State. But it's really exciting to see this sort of new field coming into action. And sometimes it's just fun to do. And that's all.
Thank you so much, Melanie. And we're going to get to the last presentation from Ricky in just a second. But if you look in the chat, you can see that there's different categories actually for this evening. We're going to open up the voting in just a little bit, but the vote is going to ask you for your opinion on who should win Astronomy Slam champion for 2020 here. And then we have some other categories too. Most thought-provoking presentation, best energy during the presentation, and most visually engaging presentation. So think about those things. But we have one more presentation, and it's perfect for the last presentation this evening. And you'll see why in just a second. Go ahead, Ricky.
All right, is it up?
It is.
Okay, so I'm Ricky. I'm going to be doing a presentation on the end of all things. So how is the universe going to end? So first, to talk about how the universe is going to end, we need to talk about how it began. So in 1929, Edwin Hubble showed that the universe is expanding. And we know that not only is it expanding, but it's expanding faster and faster. So if it's expanding, that means tomorrow it's going to be bigger. Yesterday it was smaller. The day before that it was smaller, so on and so forth. And you can just run that back as far as you want till it reaches some minimum point. And that point will be when the universe began. So we know that the universe's smallest point was what's called a singularity, an infinitely hot and dense and infinitely small point that expanded really quick. It became everything that we see today. All the galaxies and all of the matter and all the energy that produced that matter was made right then and there. So since it had a beginning, it's pretty understandable to think that it might have an end. So how could it end? When you think about it, there's really only two main forces in the universe that will determine the long-term longevity of the universe. And that's the force of gravity that we're all familiar with. That's trying to pull everything back together. And then there's some force that has to be causing the acceleration of the universe. And that's fighting directly against gravity. So when you think about those two forces, there's only three options. Either gravity is stronger than the accelerating force, so we'll get what's called the big crunch as it stops the acceleration and reverses it. Could be that the acceleration wins out over gravity, it's the stronger force, so we'll just cascade into more and more expansion, faster and faster, until we get what's called the big rip. Could also be that the very special circumstance that gravity and the accelerating force exactly cancel each other out. So then we'll keep expanding, but the expansion won't get faster and faster and faster. So we'll get what's called the big freeze. So a little bit more about each of those. We have the big freeze. This is what happens when the acceleration of the universe, it stops. So the universe is still going to be expanding, but it's going to eventually kind of run out of things to do. And this is really characterized by just 5 different stages of the primordial stage, the stelliferous stage, the degenerate stage, the black hole stage, and the dark stage. And really, the primordial stage is everything that happened before stars turned on. Energy coalesced into protons, protons started forming gas clouds. And the stelliferous stage is stars start forming. And it'll end when the last star turns off and dies. And then we'll be nothing left but degenerate matter, which is just neutron stars, white dwarfs, anything that's incredibly compact but isn't yet a black hole. And after many, many millennia, even those will themselves become black holes. We also know, though, from Hawking, that black holes don't live forever. They radiate what's called Hawking radiation. And every so often, a little bit of Hawking radiation zips off, and every time that happens, the black hole gets smaller. So after aeons, every black hole will eventually dissipate into nothing. And so at that point in time, the universe will have nothing except for a little bit of energy, some heat here and there that will eventually equilibrate. And once that happens, the energy over 1 million miles away will be exactly the same as the energy right here. And absolutely nothing can happen at that point because there are no differences anywhere. And what that's called is the heat death of the universe. The other thing that might happen is that big rip when the acceleration is just too strong for gravity to handle. So when that happens, space will start expanding faster and faster, and gravity won't be able to hold big things to each other. So galaxies and planetary systems will become unbound, and they'll just fly around the universe. They won't start orbiting around each other anymore. Eventually, the expansion of space will get so fast that molecules can't hold themselves together. And then there'll be nothing but protons and electrons running around. Eventually, it'll get too strong for even those, and all the atoms will rip themselves apart. And we also know that gravitational waves travel through space-time itself. They don't need anything else. So we can actually measure gravitational waves from neutron stars colliding with each other or black holes colliding with each other. So there's some energy requirement that space needs, and if the energy is too high, it'll rip space apart itself and the universe will die. The other thing that could happen is we get that big crunch when gravity turns out to be stronger than the universe's acceleration, and it slows it down and stops it and then reverses it. And if this happens, the universe will start getting smaller. And the farthest out that we can see into the universe is what's known as the cosmic microwave background radiation. It'll start coming at us. And when it does that, it'll gain energy and it'll start to heat up. And everything will start to look bluer and bluer as light undergoes kind of a Doppler shift, just like when a train horn comes at you, it'll just start getting more blue. And eventually it'll get so hot that stars will start colliding with each other, and they won't be able to radiate their energy anymore because they have nothing to radiate into. The surrounding area is hotter than they are. So they start to boil away. And the coolest stars, this will happen to first, and up until the hottest stars themselves can't survive anymore. And they'll all just boil away. Everything at this point in time will either be destroyed by the heat of the universe, or it'll coalesce into a black hole. And once that point hits, all we have left is for the black hole to crunch down into a singularity. At this point in time, though, the universe is dead. But what could happen is that the universe restarts in what's known as the Big Bounce. And if that happens, then it kind of turns out that the universe is eternal. It won't just keep dying, it'll just go through all of these phases. But you won't be able to know anything about the previous phase. So if this is what's happening, we'll actually have no way of figuring it out. So how will we know which of these things is going to happen? Well, there's the idea that gravity has to slow down the accelerated universe. So what would cause that? There's actually, what you can think about is some critical density that if the universe has this density, we can know which of the three things will happen. So it could either be smaller than that critical density, in which case gravity can't slow it down and we'll get the big rip. It could be bigger than that critical density, and so it'll slow everything down and we'll get the big crunch. Or it could just so happen to be equal to that critical value and we'll get the big freeze. And what you can do is you can measure that microwave background radiation for differences in the temperature, and that'll tell you what the density is once you break it down. So we've done that, and it actually turns out that we can't possibly get the big crunch. The value is too high, but it could be with our error bars that it is that critical density, or it's too big. So we could either get big freeze or the big rip. Now, there's something I didn't say about the big rip, and it's that as the universe gets bigger, whatever force is driving it to accelerate, it has to get stronger the less dense it becomes. And that's kind of a weird property that nothing that we know of has. So unless it's the strangest bit of material that we've ever heard of, it's not as likely as the big freeze. So we can kind of rule that out. So we know the big freeze is the most likely way that the universe is going to end. So I have up here is a timeline of the big freeze. And the way you read this is it's a log graph, and it's set so that 0 on this graph is right now, it's the present. So any values below 0 is going to be sometime in the past, and any values greater will lead towards the end of the universe. So what you can do is take the number on this scale and add that many zeros to the end of your number. So at 100 will be a Google years into the future. It's 1 to the power of 100. So from this, you can see that the dark era, after all the last black hole has finally died, is going to dominate the entire end of the universe. Almost the entirety of the universe lifespan will be spent doing nothing. It's a pretty long retirement. And with that, that's the end of the universe, and that's the end of my talk. I'd like to thank everybody for listening to me. That's it.
Thanks so much, Ricky. That was a perfect ending to our first annual Astronomy Slam. All right, so we're going to get you a link to vote for who you think should be Astronomy Slam champion for 2020. And then also the other categories I mentioned before and that are mentioned in the chat. Best visuals, most energy, and most thought-provoking presentation, because no one comes away from this presentation as, everyone comes away as a winner, basically. All right, Ricky, go ahead and stop sharing your screen, and we will go ahead and get into some of the questions that have been coming through the chat here. So if you have a question that you haven't put in the chat yet, go ahead and put it there. We'll try to get to it. But we got a couple questions from Brent. And Alec, he wants to know, do binary stars merge into one star eventually?
So that's a pretty good question. Short answer is I don't know. But there are some stars that are hypothesized to collide into each other. Apparently, it's a pretty rare event. It happens every like 10,000 years. There's actually one supposed to happen in 2022 that they're supposed to happen.
Yeah, we just recently talked about pumpkin stars in one of our constellation crew programs, and pumpkin stars are spinning so fast they kind of get a little squished this way and stretched out, and they look like pumpkins. And after exploring more about those, we found that they actually form from stars combining, so binary star systems combining, and all of that that spinning and all that energy goes into making the star spin really, really fast so that it squishes and becomes these pumpkin stars, which we heard from one of our constellation crew members, Nicolette, that they're pretty rare. There's only like 18 or so of these that have been discovered. So what you were saying, Alec, about how they don't really happen that often seems pretty accurate. When was the next one going to happen?
2022. I can post the link in a second here. But an important distinction, I guess, is that so the detached binary is like the one in back of me. So I mean, it's kind of detached, but you can kind of see this sort of stream thing. But you know, imagine that's not there. Is that those are sort of like the solar system. They're just orbiting around each other. The tricky part gets when they're physically touching, and that introduces a lot of friction. So those are hypothesized to maybe slow down, maybe collide eventually, but it may take a long time. But the ones that are detached don't usually collide, because that's not exactly how objects in space usually work. So they usually orbit,
Great.
unless they run into each other, which in that case we wouldn't see them. So yeah, they would turn into pumpkins.
That's a good point. All right, Belle. What would be some advice that you would give a female science major or someone who's thinking about majoring in astronomy or physics?
I think if you don't understand something, definitely ask questions and keep asking questions until you figure it out, or ask multiple people to get a different perspective on the things that you don't understand. Yeah, I don't know. I think that's the best advice, is just ask questions and keep asking them until you understand things and until you learn the things that you want to learn.
Yeah. So that's what science is about, right? Science is about asking questions. So students for sure should feel comfortable asking any question, really. That's a great piece of advice. A question just came in for Ricky. Could the big bounce could there be a big bounce after the big freeze, like another big bang?
So I kind of done you guys a disservice in that talk, where there's another idea that involves quantum mechanics that I didn't mention. So the answer is yes, because there's the idea in quantum mechanics of like this thermal soup where you can create particles out of nothing as long as you create a particle-antiparticle pair. So you've actually added absolutely zero energy to the universe. And if in that case, there is a chance that before infinity, another Big Bang just spontaneously happens somewhere. So it's not like it's going to bounce again, but there is a possibility of another Big Bang just happening.
Great. All right, Melanie. Let's see. We don't have any questions in the chat for Melanie. We have a lot of thank yous and everything, but I have a lot of questions. I always will. Let's start with an easy one. How did you pick this topic? Science, the sound of science.
I came across like a video or a playlist of like spooky Halloween sounds that NASA put out, which were some of those recordings that you actually heard, especially the Saturn one. But it got me really interested. I was like, well, I've been told my whole life there's, you see things that are exploding and making big sounds like in movies and games, but then in my classes I was learning there's no way, there's no sound in space. And so it was kind of frustrating to me and confusing, and I really didn't understand it for the longest time. So it was a way for me to honestly educate myself more on it, and a lot of other people I think have the same kind of questions or misconceptions. And anytime we can clear up a misconception about space or science, I would love to do that.
Yeah, that's great. All right, Alec, back to you. Why are binary stars so common?
That's another really good question.
So think about how they form, right? Out of molecular clouds.
Yeah. So you have a molecular cloud and whatnot. Chances are every once in a while you're going to have one that's in, maybe not every once in a while, very often in a while, you have just two blobs that are forming into big things called stars. and whatnot.
And they're like as a group, right? So you have this huge cloud and there's a lot of stuff in it. So there's maybe gonna not just be one star forming, but another star next to it and another one next to that and so on.
Mhm.
So
Yeah, but that's a good question. I don't know if I have a great answer.
yeah, is the sun a binary?
No, because it's just one.
But is it?
It's just one star.
But do we know that for sure? Because they're trying to find it, right? I think they're trying to see if there is something that's gravitationally bound to our sun. We haven't found it yet. Do you think it's by itself?
Yes.
Yeah, I think it is too. All right. Belle, back to you. What's your favorite scientist?
I don't know. Doing this research, I really like Jocelyn Bell Burnell. She's done a lot of TED Talks and a lot of interviews, and I just want to say I'm pretty obsessed with her. I talked to my sister about it, and I was like, hey, I'm going to buy a bunch of stickers. Do you want some of her? Because I'm completely obsessed now, and I need people to know about her. So probably Ms. Burnell.
Nice. There are so many votes coming in, and I'm watching them come in, and it's really great. There's a lot of comments too, and so when I said there's a lot of thank yous, they're coming in through the comment form or through the Google form to vote, and they're saying that everyone was great, and well done, great presentations, great job everyone, very informative presentations. Someone was biased for their nieces, fantastic presentation, and a lot of other amazing comments here. So people have really enjoyed this, and we're going to actually keep the vote open for a while. We're going to keep it open for another 24 hours so that people can watch this later and vote when they get the chance to watch this. I am a little confused though, because we are having a lot more votes than who's watching live right now. So I'm interested in seeing how this all turns out. I think there's some family members who are really excited for their relative here. All right, but we have a lot of great votes coming in for everyone, and it's really exciting. Questions. I have more. Let's see. Ricky. There was another question in the chat from Brent. What's the force causing the expansion of the universe to to expand and then also to be accelerating?
Okay, it's gonna sound like a cop out, but I don't know, and no one knows. So since it's accelerating, there has to be something doing it, and we just kind of call the thing doing it a blanket term called dark energy. And
it's like
something
we
like
can't
the
see
big
it. We don't know what it is. It's dark, right?
Yeah, it's because we don't know what it is, and it's something that we can't see, so we call it dark. That's the reason dark matter is called dark matter, because there is gravity from something. Matter causes gravity. Well, matter interacts with the force that we know is gravity, and we can't see it, so we call it dark. Same thing with the energy that's driving the expansion. Another thing, though, like for the big rip, I kind of mentioned that it would have to have specific properties. So since we don't know what the dark energy is, it could be a bunch of different things. And there's one version of it with very specific physical properties that we call, has the moniker phantom energy, which is kind of neat. But we could look that up. And that's the type of energy that the more spread out it is, the stronger it is. Which is kind of a weird thing. We don't see anything like that, but it's not impossible. And that could be what's causing it. And if that happens, we'll get the big rip. I hope that answered the question. And the answer is no one knows.
Again, what science is about, finding the answers to really, really hard questions.
Yeah, there's a lot of people way smarter than me working on that.
Yeah. Yeah, and some people say that, the hardest part of science isn't answering those questions, it's asking those hard questions to begin with. So, all right, Melanie, back to you. What are some applications of data sonification?
So besides it just being kind of fun, I talked a little bit about the sun. And we know that the sun has many, many layers. And again, the sun's just like most other stars, or other stars are similarly kind of constructed. So obviously we can't see inside the star, we just see light. We're lucky, honestly, that we can even see that because of how far away some of them are. But because of this sort of layering, we know there's more to it, but it's really hard to study it. Obviously we can't go there, we can't send things there, we can't see through it magically. So using these sort of waves and interpreting them into sound is a way that we can kind of deconstruct the inner contents of a star, again, like our sun. So it's just a way to kind of look inside of things that we otherwise wouldn't be able to. I've seen it mostly used in studying stars more than other things, but it can also be used for like weather patterns, again, and like changes in magnetic fields and things like that.
It's interesting. Because can we pick up information with our ears that is really hard to decipher with our eyes?
Yes, because a lot of times, again, like we can't see things happening, like with black holes, for example, but we know we see these kind of waves being transferred out. So again, like with LIGO discovering this merging of black holes, we couldn't actually see the black holes, but we could tell what was there and what was going on just based on those gravitational waves.
All right, so we got a question in from Messenger, actually, from Melanie. Do black holes themselves have a sound different from the sound of them merging?
So technically, I guess yes. It's mostly seen in those waves outside of the black hole. So obviously, if light can't escape a black hole, certainly sound can't escape a black hole. But there are waves happening in the gas and dust surrounding the black hole, which again is converted into sound, or actually is making a sound, like that one in the Perseus cluster, for example, but we cannot hear it.
Yeah, so and it's not like it's kind of the black hole, but not really, because it's the stuff going around the black hole, the accretion disk of, yeah, that is affected, yeah. I have all my questions are for Melanie right now. But this one I'll actually open it up to everyone, but it was inspired by Melanie's. So we evolved as humans to have the ability to see, a lot of us anyway. And then we also evolved to be able to hear. So why do you all think that we did both of that? And like, how did we evolve to hear in the first place? I know we're not biologists, but let's just go with it. Anyone?
Well, let's see. What's the first thing that could see? Probably some bug 500 million years ago.
Some like underwater, probably underwater organism.
Yeah. Let's see. Let's bring it back.
My thinking for this is that a lot of organisms would start in the water, obviously, and if you're not in the top zone of the ocean, for example, you can't see very much anyway, because water can't penetrate that deep. So you have to have other forms to identify things that isn't just visual. So forming that ability to decipher different waves in the water, I think, would be more beneficial than having visuals at first. So I think visual would have developed later.
Yeah.
Belle.
That's a great answer.
Yeah, I'll second that opinion. Anything that stops you from getting eaten is a good thing to have.
Yeah.
So it just means, like, if you have it, you make more babies.
Survival of the fittest.
Yeah, if you just think about it, eyesight is incredibly powerful because it allows you to,
But it's only
for
really
lack of a better
powerful
term,
when there's a location that you could see things though too.
Well, right, yeah.
Develop
So,
later.
Yeah.
right, if it's light, but it allows you to basically scan the physical nature of your surroundings. But it's why we have hearing and sound, and sight, is because everything back until fish, has that. So.
All right, we got another question in the chat for Ricky. Sir Roger Penrose claims there is evidence of an earlier universe before the Big Bang. Any thoughts on that?
I don't know what he says about it. I haven't actually read what he said about it, so I can't form an opinion on it right now.
Someone read a paper where there's evidence, perhaps there's evidence of previous black holes in the background microwave radiation, like from a previous universe, like an echo. I'm not familiar with this either, so.
I'm not familiar with that, but I don't know if that's what they're talking about, if that would say anything about a previous universe, because the cosmic background, not the cosmic background, the CMBR
Yep.
is the farthest we can see with visible light, but it's not the exact beginning of the universe. So we don't
Exactly.
really know right now what happened directly after the beginning. So I don't know how you can make a claim before that.
Yeah, we know what happened very soon after, even
Yeah,
beyond the cosmic microwave
yeah, but we don't
background
know what
radiation.
happened when
Right.
inflation started.
Yeah. It was
Prior
just
to
the
that. I
the
think they're
early
teasing
universe
stuff
was
out.
so the early universe was just so dense that light couldn't actually escape the density
Yeah.
of it. So yeah.
So I'm sorry, but I don't know what he said, and that is probably the limit of my knowledge on the subject.
This is good though. Like these are definitely thought-provoking questions that will help inspire us to do some more research on our part. But there's so much that we can't know everything. All right. Well, I could go on for a long time asking questions, but I won't. I'm gonna turn it over to you all. If any of you, Alec, Belle, Melanie, or Ricky, have any questions for each other, go ahead.
Melanie, out of all the sounds that you had found, which one was the most intriguing to you, or you thought was the most interesting and unexpected?
I really thought the Earth one was interesting, honestly, because I never imagined the Earth having like a sound or emitting light, or I know it's light that we can't see, but it still kind of is. As well as because we actually use radio transmissions on Earth, we are seeing that kind of interference. So that I think is what those little kind of chirping sounds were. So I thought it was kind of musical and fun, and I liked it.
Singing. It's kind of like the planets are singing. Yeah. Any other questions? We've heard from Melanie a lot. Let's do Alec on this one. Alec, will you please let people know about what we do Friday evenings?
Yeah, so every Friday evening at 6:30, we do what's called Constellation Crew, and we pick a constellation that's going to be visible at the time, and we talk about not only just the constellation itself, but also cool things inside of the constellation, cool stars, exoplanets, nebulae, etc. Yeah.
Yeah, we do that Fridays at 6:30 here live on Facebook. So check us out for that. If you're watching this later, make sure to find the link to vote for the Astronomy Slam champion and the other categories that we have. But let's wrap it up there. Thank you so much, everyone, for tuning in. And thank you, Alec, Belle, Melanie, and Ricky, for your amazing presentations. You're amazing. Thank you. All right. Have a good night, everyone, and a wonderful rest of your weekend.